As recently as 25 years ago, pneumatic control systems for heating, ventilating, and air conditioning consisted of a limited variety of controllers, relays, and control devices. In the late 1960s, the pneumatics industry was revolutionized by the introduction of the pneumatic transmission system. What was a revolution then is a common and important element of today's complex and sophisticated HVAC systems. My name is Steve Drollinger, and I'm an HVAC systems instructor at Johnson Controls Institute. The purpose of this video program is to provide you with a working knowledge of pneumatic transmission systems. Together, we'll cover the following main points. First, we'll look at the differences between pneumatic transmission systems and conventional control systems. Second, we'll view the physical operation of a standard pneumatic transmitter. Third, we'll look at control terms and equations which relate to pneumatic transmission systems. And finally, we'll set up a typical application using common pneumatic transmission components and concepts. Let's begin by looking at differences between two alternative approaches to a simple application. The application calls for discharge temperature control of a heating coil. In the conventional approach to this application, a controller is used to measure the variable, temperature, and to produce a control signal to the valve. The set point and sensitivity of this control loop are established on the controller. Now let's look at the pneumatic transmission approach to the same system. In this case, a temperature transmitter measures the variable and sends a pressure signal equivalent of that measurement to a receiver controller. The receiver controller compares that signal with its set point and produces an output signal based on that comparison. The receiver controller establishes the set point and system sensitivity for the control loop. In fact, the only difference between these two approaches is that the transmitter takes the place of the sensing element in the conventional system. Both systems are equally capable of controlling the discharge temperature of the coil, but yet the pneumatic transmission system requires a combination of two devices to control the valve, where the conventional controller acts alone in this system. Certainly there must be some advantages of the pneumatic transmission system. Otherwise, all systems would use conventional controllers because of the simplicity of the system. What are these advantages of pneumatic transmission systems? Well, first let's look at the distance between the controller and the measuring element in both systems. In the case of the conventional system, the distance between the controller and the point of measurement is limited by the length of the capillary, which transmits changes at the sensitive portion of the element to the controller. In most cases, the capillary has a maximum length of 25 feet, which means that the controller has to be mounted within 25 feet of the point of measurement. This is not conducive to centralization of control. How about the pneumatic transmission system? In this case, the temperature measurement taken at the element is converted by the transmitter to an air pressure equivalent. That pressure, referred to as transmission pressure, can be transmitted effectively over an extremely long distance, up to 1,000 feet and sometimes more. So the first benefit of pneumatic transmission systems is that the measurement signals can be transmitted over long distances. This benefit leads into the second main benefit, which is centralization of control components. Because the controller doesn't have to be located at the point of measurement, it can instead be located in a central control panel, along with all the other controllers, relays, and auxiliary devices. This is especially helpful for monitoring during troubleshooting, when it's necessary to know the status of several different variables and control signals at once. Also, all of the set points and adjustments for the whole system can be localized in one panel, rather than having to visit each individual conventional controller location. From this location, I can see every individual controller output and input. In order to demonstrate the third key benefit of pneumatic transmission systems, let's add one more requirement to our original application. We started out requiring control of discharge temperature. Now we want both control and indication of discharge temperature. Going back to the conventional system, where can we install a gauge that will provide indication of the temperature measured at the element? Well, there's only one variable pressure in this system, and that is the controller output. Can the controller output be used to indicate temperature? The answer is no. There are three variables that can change the output pressure. First, the temperature at the element could change, causing a change in output pressure. Second, a load change could occur, which would cause the output to change, but the temperature would remain nearly constant. The third variable is that the set point of the controller could be changed, which would again cause a change in output not related to a change in measured temperature. The conclusion is that in this conventional system, there is no pressure which has a constant temperature equivalent. Moving to the pneumatic transmission system, can we find a pressure signal that can only be affected by a change in temperature? Yes. Remember that the transmitter simply converts a change in measured temperature to a change in transmission pressure. Its whole purpose in the system is to achieve a constant temperature to pressure relationship. Since a transmitter has no set point, a set point change alone can't affect it. So by matching a pressure gauge to the calibrated range of the transmitter, any transmission pressure can be converted by the gauge to a temperature equivalent. So the advantages of pneumatic transmission systems can be summarized by, first, transmitting measurement signals over longer distances. Second, allowing for centralization of control components. Third, providing indication of measured variables. The advantage of pneumatic transmission systems can be more clearly understood when we look at the operational differences between controllers, transmitters, and receiver controllers. First, let's concentrate on the similarities and differences between controllers and transmitters. By comparing these two categories of instruments with their covers removed, it is rather difficult to even tell them apart. Here is a T4002 room controller and a T5002 room transmitter. Here is a low volume output remote element controller, a T3610, and a low volume output remote element transmitter, a T5210. And finally, a high volume output remote element controller, a T8000, and a high volume output remote element transmitter, a T5220. Note that the high volume devices are two pipe instruments, that is, separate supply and output, while the low volume devices are one pipe instruments which require a restricted source of supply. What differences do you notice between the controller group and the transmitter group? Well, the most conspicuous difference is that all the instruments in the controller group have set point dials. The transmitters don't. Less noticeable is that each of the controllers has a sensitivity slider adjustment. The transmitters, on the other hand, have a dab of red paint on the sensitivity adjustment. This indicates the sensitivity was precision calibrated at the factory and should never be tampered with. Now let's review the functional differences between controllers and transmitters. These controllers are calibrated for each individual application to provide a certain output pressure within the spring range of their controlled device, sensitivity is also calibrated for each individual application. These transmitters, on the other hand, don't know what the spring range of the controlled device is. Transmitters don't need to know these system parameters because they're not controlling anything. They're merely taking a measurement and passing that measurement along to the receiver controller in the form of an air pressure signal. The receiver controller must be calibrated in much the same way as a conventional controller. That is, it must be calibrated to achieve the set point and the system sensitivity. Now that we've seen the differences between pneumatic transmission systems and conventional control systems, let's move on to the actual operation of the pneumatic transmitter. Since the most common transmitter type is the T5210, we'll take a look at a cross-sectional drawing of the instrument to explain its operation. The T5210 illustrated here is furnished with a liquid-filled bulb-type sensing element. As the temperature surrounding the bulb increases, the liquid inside the bulb expands. This expansion is transmitted through the capillary up to the receiver diaphragm. The increase in pressure caused by the expanding liquid causes this lever to rise. As the lever rises, the back end of the lid is allowed to rise along with it. As the back end of the lid rises, the front end of the lid moves down closer to the control port. This movement restricts the exhaust rate of air out of the control port, causing pressure to build up in the transmission line and ultimately to the receiver controller. Once the transmission line is filled up, back pressure fills up the negative feedback diaphragm, which results in an upward force. This upward force will raise the lid off of the control port slightly to stabilize the transmission pressure. This negative feedback feature is characteristic of all pneumatic proportional devices. Once the proper transmission pressure is reached, that constant pressure is trapped in the transmission line, and the only airflow path is between the restrictor and the control port. The restrictor is needed here to reduce the volume of air so that the exhaust rate is manageable by the small control port and lid. It is also very important to emphasize that once the transmission pressure is reached, the transmission line is static, meaning that no flow is taking place through the line. This is important because when there's no flow, there are no pressure losses, which means that the receiver controller gets the full, true transmission pressure. The only flow that takes place is between the restrictor and the control port. So it is important to locate the restrictor as close as possible to the transmitter. This minimizes the distance through which the flow travels and subsequently minimizes the pressure losses. In applications where transmission lines are extremely long and where fast response time is critical, you may consider using a high volume output transmitter. It produces the same signal as the low volume transmitters, but much faster. Now that we've seen the physical operation of the transmitter, let's take a look at its specific output characteristics. This graph illustrates that all pneumatic transmitters exhibit a linear 3 to 15 psi output pressure with respect to the calibrated range of the instrument. So, a 0 to 100 degree transmitter would send out 3 psi at 0 degrees and 15 psi at 100 degrees. Every different transmitter range has a different temperature to pressure equivalent. So we need to know the range of the transmitter in order to make predictions on what the pressure should be at any measured temperature. This list describes all the standard sensing ranges for Johnson Controls temperature transmitters. Do you notice a pattern of how they're grouped together? They're all grouped according to their span, or the difference between the upper and lower limits of the temperature range. So if we know the range of the transmitter, we can also determine the span. And once we know the span, we can make the key calculation, which is sensitivity. Remember that sensitivity tells us the relationship between a change in temperature and the corresponding change in output pressure. The expression for sensitivity is change in pressure divided by change in temperature, or psi per Fahrenheit degree. Since we know that all transmitters exhibit an output pressure change of 12 psi, that is the difference between 3 and 15, then all we need to do is divide 12 psi by the span of the transmitter. Looking at this category of ranges, we can see that even though the ranges are different, the spans are all the same. So 12 psi of pressure change divided by 25 degrees of temperature change gives us a sensitivity of 0.48 psi per Fahrenheit degree. In other words, for each additional degree of sensed temperature, we will see an additional 0.48 psi of transmission pressure. Let's go on now and calculate the sensitivities for the other span categories. In this category, we again take 12 psi of pressure change divided by, this time, 50 degrees of temperature change, or 0.24 psi per Fahrenheit degree. In this category, 12 psi divided by 100 degrees of temperature change, which gives us 0.12 psi per Fahrenheit degree. And finally, in this category, 12 psi divided by 200 degrees of temperature change, or 0.06 psi per Fahrenheit degree sensitivity. With these sensitivity values, we can now make precise predictions on what the transmission pressure should be at any sensed temperature for any given transmitter range. Take the example of a 0 to 100 degree transmitter sensing a temperature of 60 degrees. What would be the corresponding output pressure? Well, the first step is to determine the span of the transmitter, which is 100 degrees. Next, divide the span into the total pressure change of 12 psi, again, the difference between 3 and 15, to get a sensitivity of 0.12 psi per Fahrenheit degree. For each degree above the bottom of the range, we should have 0.12 psi. So we can multiply 0.12 times the temperature difference between the bottom of the range and the actual sensed temperature. Since the bottom of the range is 0, and the difference between 60 and 0 is 60, we find that 60 degrees times 0.12 psi for each degree equals 7.2 psi. Now we have to add the starting point to this calculation. Since the transmitter is already sending out 3 psi when it's sensing 0 degrees, the final output equals 10.2 psi. Let's review the steps involved in making this calculation. First, identify the range of the transmitter. Second, based on the range, identify the span. Third, based on the span, calculate the sensitivity. Fourth, determine the difference between the bottom of the range and the actual sensed temperature. 5. Multiply the results of the previous two steps. And finally, step 6, add 3 psi to the answer in step 5. Using these 6 steps, we can calculate a transmission pressure equivalent for any sensed condition, whether it is temperature, pressure, or relative humidity. Here are 2 sample problems for you to copy down and solve. Take 5 minutes to copy the problems and calculate the pressure equivalence. Problem number 1. A minus 40 to 160 degree transmitter is measuring a temperature of 60 degrees. What is the corresponding transmission pressure? Problem number 2. A 30 to 80% relative humidity transmitter is sensing a relative humidity of 50%. What is the corresponding transmission pressure? Please pause the tape now and restart the tape after you've completed the calculations. Let's check your calculations. In problem number 1, the range was identified as minus 40 to 160. The span equals the difference between the upper and lower limits of the range, or 160 minus a minus 40 equaling 200 degrees. The next step is to divide the span into the 12 psi transmission pressure change, giving us 12 psi divided by 200 degrees, or 0.06 psi per Fahrenheit degree. Now we need to determine the difference between the actual sensed temperature, 60 degrees in this example, and the bottom end of the range, minus 40 in this example. 60 minus a minus 40 equals 100 degrees. Next, we multiply the temperature difference, 100 degrees, times the sensitivity, 0.06 psi per degree, which gives us 6 psi. The last step is to add the 3 psi starting point to the previous calculation. 6 psi plus 3 psi equals 9 psi. So 9 psi is the pressure equivalent to 60 degrees as sensed by a minus 40 to 160 degree transmitter. In problem number 2, the range was identified as 30 to 80% relative humidity, resulting in a span of 50% RH. 50% divided into the 12 psi pressure change yields a sensitivity of 0.24 psi per percent relative humidity. Next, we must calculate the difference between the bottom of the range and the actual sensed humidity. 50 minus 30 equals 20% RH. Multiplying this difference times the sensitivity, we get 20% times 0.24 psi for each percent, or 4.8 psi. Finally, we add the 3 psi starting point to get a pressure of 7.8 psi. So a 30 to 80% RH transmitter will transmit 7.8 psi when sensing 50% relative humidity. Now that we understand control terms and can make predictions about temperature and pressure equivalence through equations, we will move on to the final point of this presentation. Specifically, we'll set up and calibrate a control loop. Going back to our original example, we'll use a pneumatic transmission system to control for a certain discharge temperature. The purpose of the transmitter is to measure the temperature. The purpose of the receiver controller is to control for that temperature. The set point is 55 degrees. The transmitter range is 0 to 100 degrees. The controller gain will be 8 to 1, and the valve actual spring range is 4 to 8 psi. How would you go about setting up this combination of components to achieve this control loop? Let's follow the 4 steps of adjustment. The first step is to measure the temperature at the element, and let's say we find the temperature to be 55 degrees. What transmission pressure will correspond to 55 degrees? Following the previous guidelines, we need to know the transmitter sensitivity, which is 0.12 psi per degree. So 55 degrees times 0.12 equals 6.6 psi, plus again the 3 psi starting point, giving us 9.6 psi. The next step in calibration is to turn the set point dial to match the actual temperature. When I go to turn the set point dial, I find that there are no numbers, just 50 blank graduations. So how do I know where to position the dial? On any receiver controller, the set point dial gets its numbers from the particular transmitter range being used. Since we're using a 0 to 100 degree transmitter, this becomes a 0 to 100 degree set point dial. The first and last graduation on the set point dial always correspond to the upper and lower limits of the transmitter range. What is this dial set for right now? Since it's at the middle graduation, it's set for the temperature halfway between 0 and 100, or 50 degrees. How many degrees are represented by each graduation on the dial? I'm spreading 100 degrees of temperature change over 50 blank graduations. So 100 degrees divided by 50 graduations gives me 2 degrees per graduation. Going back now to the second step of calibration, we want to position the dial for 55 degrees. The dial is at 50 degrees now, so I want to increase by 2 1/2 graduations, or 5 degrees, to change from 50 to 55. Now we're ready to execute the third step of calibration. That is, to produce an output pressure equal to the pressure noted in step 1. Since this is the first time calibrating this controller and we don't have anything to relate to from step 1, we will choose an output pressure in the middle of the spring range. Our spring range is 4 to 8 psi, so we'll calibrate the output to 6 psi. For this particular type of receiver controller, the output adjusting screw is located inside of the set point dial. Since the dial is already calibrated, I need to change the pressure without changing the position of the dial. So, I'll loosen the dial set screws, turn the output adjusting screw to produce 6 psi, and finally tighten the dial set screws. The last step of calibration is to turn the set point dial to the desired temperature. In our example, the dial is already at the desired temperature, so our sample calibration exercise is complete. It's important for you to understand that if we had used a different type of receiver controller, such as a T9000, the 4 steps of calibration would remain the same. The only difference is that the T9000 has an output pressure adjustment which is independent of the set point dial. Now that this control loop is calibrated properly, what predictions can we make about how the devices will respond to a change in temperature? Let's say the actual temperature goes up from 55 to 56 degrees. How does the transmitter react? When the temperature was 55 degrees, the pressure from the transmitter was 9.6 psi. Since the transmitter's sensitivity is 0.12 psi per degree, if the temperature goes up 1 degree, the pressure will go up 0.12 psi. So the new transmission pressure will be 9.72 psi. The next important question to answer is, now that the transmission pressure has increased, how will the receiver controller react? To answer this question, we must consider the controller gain. In this example, the controller gain is 8 to 1, which means that the output of the controller will change by 8 psi for every 1 psi change in transmission pressure. So the gain, in effect, multiplies the input change by 8. If the input goes up by 0.12 psi, the output goes up by 8 times that amount, or approximately 1 psi. This relationship between transmitter sensitivity and gain is expressed by a term called system sensitivity. System sensitivity equals the transmitter sensitivity times the gain. In our example, 0.96 psi per degree. The system sensitivity predicts how much the output pressure will change based on a 1 degree change in temperature at the transmitter. Knowing the system sensitivity allows us to establish a throttling range, which is defined as the total temperature change necessary to completely modulate the valve from fully open to fully closed. The mathematical expression for throttling range is spring range divided by sensitivity. In our example, the spring range is 4, that is the difference between 4 and 8 psi, divided by the system sensitivity of approximately 1. So the throttling range is 4 degrees. Graphically, this throttling range can be shown this way. If this throttling range is too wide, an increase in gain will cause the throttling range to tighten up. For example, if the gain were increased to 16 to 1, what would be the new throttling range? First, we need to calculate the new system sensitivity. That would be 0.12 times 16, or approximately 2 psi per degree. Now we divide the spring range by this new system sensitivity to get 4 pounds divided by 2 degrees, or a throttling range of 2 degrees. As in any proportional control system, we would attempt to achieve the highest sensitivity possible without producing cycling in the system. Let's review the concepts and components of pneumatic transmission systems. We started out by looking at the differences between pneumatic transmission systems and conventional controllers. Advantages of pneumatic transmission systems were found to be centralization of control components and availability of temperature indication. We compared the physical and functional differences between controllers, transmitters, and receiver controllers. We watched the physical operation of the transmitter. Then we looked at calculations to help us make predictions of proper transmission pressure for any transmitter range at any sensed temperature. Next, we set up a pneumatic transmission system and followed the 4 steps of calibration using the blank 50 graduation set point dial. And finally, we examined the relationship between the transmitter and the receiver controller. We defined gain, system sensitivity, and throttling range to help in understanding the operation of the system. I hope this videotape has helped you to understand your pneumatic transmission system, and I encourage you to view other HVAC training packages available from Johnson Controls Institute.